Margaret Baggio, the Program Manager for Education and Outreach for NASA's Texas Space Grant Consortium. Welcome to the STEM Enhancement in Earth Science presentations. We are very fortunate today to have our Moon Exploration team to start us off. And we appreciate Dr. John Gruner of NASA Johnson Space Center being the mentor for these students. This was our first test in having a remote scientist and engineer working with the C students as they are here on the campus at the University of Texas. So Moon Exploration team, come on up.
Hi, we're the Lunar Exploration Group. My name is Shara Allen.
I'm Prachi Gautam.
I'm Sebastian Perez Lopez.
I'm Ian Slow.
And I'm Maya Taff.
So the area of our interest is going to be the lunar South Pole. Now this area is interesting for a couple of different reasons. The sunlight hits the surface of the moon at an oblique angle that's almost perpendicular at this region, which causes the light to barely graze the surface. This causes peaks of eternal light, which you can see here as the topographical regions in red, orange, and yellow, and cold traps, which are the regions in blue and purple right here. So these are topographical lows as they are craters, and the peaks are topographical highs. And as you can see, the temperature ranges from very, very hot to very, very cold. And the cold traps are cold and dark at like 25 Kelvin, and the peaks of eternal light get almost nearly constant illumination. So why is this even relevant? Well, the cold traps have been shown to harbor water ice. Water is an essential space resource, and it's something that a lot of space agencies and private companies are going to be vying for. So evidence has shown through neutron spectrometry, radar reflections, and LCROSS that this ice and water actually does exist. So the first thing that they did is that they detected excess hydrogen in this region, and they figured that that could be conducive to water. It wasn't confirmed that it was actually liquid water, so they had to do 2 more experiments with radar reflection and LCROSS. The radar reflection showed that the water that reflected back up to the surface of the radar was in fact going to be H2O. And LCROSS was a satellite that impacted in a crater, and the plume vapor that came up showed that there was water vapor in that ejected plume. So there is water on the moon. That's something that we know. And now that we know that, a lot of space agencies and companies are going to be on the moon in the next 10 to 15 years with their lunar rovers mining for ice. So these rovers are going to need energy, heat, and a water storage facility. And that's something our company, Lunartix, wants to provide to them. And they're going to have to buy from us because it's simply too much of an infrastructure investment for them to get their own energy, so we want to be the first to provide that to them. So this is our basic concept of operations. Our users, as I mentioned before, are going to be the space agencies and private companies that have their rovers on the moon. And they have a need for the power, heat, and water storage as it does get very cold and very dark on the moon at times. So that's something we're going to provide for them. And how are we going to do that? With our robots that will assemble our stations in thermal Malati, which is something we'll further explain, and our mission control back down at Earth. And we also have element designers using CAD software that will design the various elements of our station.
So this is our decision tree, which shows the thought process of our company to create the best lunar utility station. So first we're going to talk about power. So before we can start, we had to figure out how much power the rovers will need. So we based our rovers off of a Ford Ranger 2011 pickup truck, and we found that the minimum power needed was 5,000 watts, and the wet mass power would be 9,000 watts, and we got that from calculating how much the max amount of ice deposits they can hold. So first we tried to use laser power beaming to power the rovers, but our technology is not up to par currently. So currently laser powers only travel 1 kilometer, which is not far enough for us. So then we tried solar power panels. On average, majority only have 22 to 23% efficiency, and the most power efficiency one's 50%, so it's still not as efficient as we would like. And we also had to consider lunar dust, which would cover the panels over time lowering the efficiency even more. And we had to consider laws of thermodynamics. So as the heat increases, the output decreases. Then we tried RTGs and MMRTGs, which use the decay of plutonium-238 to create electricity using thermocouples. And they only create 110 watts of electricity, which is not enough because we would need at least 45 just to power one rover, and they're $36 million each. So we ultimately went with fission-based nuclear reactors, which provide 40 kilowatts of power, and they use uranium, which is much more abundant in the Earth's crust.
Okay, so I was in charge of looking at our power requirements to determine how big a battery we would need and what kind of battery we would need. So I decided to go with lithium-ion batteries, the same kind of batteries that are used in the Curiosity rover. In order to find out what its mass would be, how much space it would take up, I had to find out certain specifications of the lithium-ion batteries. So I ended up finding things like specific energy, which is 265 watt-hours per kilogram. That'll give me what the mass will be of the battery that we need. I found energy density, which is 693 watt-hours per liter. That will give me how much space it would take up. And then I found what the cost would be and the charge efficiency. So what I ended up calculating that was based on the range that the rover needed to go, which is 80 kilometers, and a 32-hour drilling time. We would need a 224 kilowatt-hour battery. The battery would take up 323 liters of space, and the mass of the battery would be 845 kilograms, and it would cost $89,600. So since our nuclear reactor provides 40 kilowatts of power, and we'll have 5 charging stations on our main base charging station, each battery will be able to have 8 kilowatts of charging power, which would make each battery take 32 hours to charge. And this is the design of the charging station I came up with.
Okay, so now I'm going to talk about Malati. But before I do that, I'd like to speak a little bit about the lunar environment. So firstly, the lunar regolith, which is a fine rocky dust that covers the surface of the moon, it has a pretty high thermal contact resistance, which means that the temperature of the regolith won't change too fast. So in other words, it has a pretty high specific heat. Secondly, the regolith has a low thermal diffusivity, and that means that any heat that goes inside the regolith, the quantity at which it will diffuse out to colder areas will be really low. Those properties I just mentioned will be pertinent in a later explanation that will come later on in the presentation. So unlike the Earth, the moon lacks an atmosphere, and any heat that does go into the moon, it will be lost and radiated out into space. So that leads to extreme temperature swings. So the temperatures can be as low as -200 degrees Celsius and rise up to -50 degrees Celsius on the poles. And on non-polar areas, it will be as low as -150 degrees Celsius and rise up to 100 degrees Celsius. And this is a chart kind of explaining the temperature swings on the moon's south pole, since that is what we're focusing on. The redder areas show that during the daytime, temperatures can reach up to 300 Kelvin, and during the nighttime, which is the picture on the right, temperatures can be as low as 25 Kelvin. So Malati, what is it? Malati is a device, an insulating umbrella that provides heat and protection to electronics or rovers when the night and temperature will fall on the moon. Why should we consider it? Well, soon in the near future, there's going to be a lot of prospecting rovers searching for and extracting materials on the moon. And we have to consider that there is 14 days of night, and during the nighttime, it does get to as low as -200 degrees Celsius. And unfortunately, rovers or electronics cease to work at -55 degrees Celsius. So with these warming safe havens or the Malati placed on the moon, the productivity and work time of the rovers will be maximized. So here's the materials to consider when building the Malati. You want to use a lightweight metal so that the payload from the Earth to the moon isn't too heavy. You'd also not only want to consider using a solar reflector or mirror, but a tracker as well, since the sun hits the moon's poles at a very oblique angle. And lastly, we need a thermal pad or mass, and we would produce that from using native regolith. We can't use native regolith because it's not really a good candidate, and I'll explain that later. So how does it work? As you can see here, there's two pictures. One represents how the thermal body operates during the daytime, and the bottom one represents how it operates during the nighttime. So during the daytime, the umbrella will lift up and angle itself so that the sun will hit the solar reflectors, which are located at the bottom of the umbrella. It will hit the solar reflectors and reflect onto the thermal pad. As that is happening, the thermal mass will store any of the heat that is put onto it. At night, thermal mass will radiate any of its heat up to the rovers, therefore warming it, and the solar umbrella will come down and insulate any of the heat that is radiated from thermal mass. So earlier I said that lunar native regolith isn't a really good candidate for our thermal mass, and here's why. Earlier I mentioned how native regolith has a really low thermal diffusivity compared to the basalt rock, which will mimic our thermal mass on the moon. So since the basalt rock has a higher thermal diffusivity, more heat will diffuse out to colder areas at a higher quantity, and it also has a lower specific heat, which means that it'll get hotter quicker than a native regolith. I'd also like to mention that the basalt rock also has a higher thermal conductivity, and that just means that the heat will flow out of thermal rock at a higher rate than it does in a native regolith. So overall, the basalt rock, or our modified regolith, is a better candidate because it diffuses heat out at a higher quantity and a higher rate, and it gets hotter much quicker. So we decided to turn our thermal body into a rest station where rovers will be able to rest, get warm, protection, and store any of the materials they get on the moon. And we decided that each station will have 6 parking spaces, and each parking space will have access to 2 storage compartments. So when it comes to dimensions, as I was designing the thermal body, I had to keep in mind that I didn't want to make it too big because it had to fit in a specific area that Sebastian gave me. And I didn't want to get too small because you want to fit as many parking spaces within a station as possible, but you also want to give the rover enough space to park in. So I decided that each station would be 22 meters squared, each parking space would be 6 meters squared, the storage compartments will be 22 meters cubed, the umbrella will be 22 meters squared, and the height of the thermal body will be 10 meters. This is a depiction of what the thermal body will look like on the moon. At the bottom, these squares represent the thermal masses where the rovers will park on and stay. The top, this represents the insulating umbrella, and the squares that are on the rectangular prism that's in the middle, those represent the storage compartments where the water or ice will be stored. And this was made by Ian on CAD.
Right, so none of this really matters if you can't find a good location to put both the energy site and the thermal body site to operate at its max efficiency. But before I begin with how I chose the locations for both these sites, I want to talk a little bit about the Lunar Reconnaissance Orbiter Quick Map. Basically, it's a map of the entire lunar surface taken by the Lunar Reconnaissance Orbiter camera, and I was able to overlay maps about polar illumination, soil saturation, rock abundance, and also find the distance between 2 points and use this for elevation graphs, which I'm going to use later. So what determines the location of a utility site? I actually used 2 criteria, the first being the nearness to predicted resource sites, whether it be water, polar volatiles, or any other resources that you're planning to drill in the future. I also had to look at the topography of the nearby area, because if I put the energy site at the top of a mountain or at the bottom of a crater on the side of a really steep slope, it's really not going to be of use for these rovers. So the area that I chose had to be relatively flat and relatively easy to get to. So when it comes to the nearness to predicted resource sites, I used these 2 maps. The one on the left shows the albedo ratio of the lunar surface, and basically anything that you see in light blue shows albedo ratios that are equivalent to those of water ice. And albedo is just the reflectivity of the sun. And then I just found 3 areas that I thought contained a lot of possible water ice, and I grouped them together. And then the picture on the right shows the sublimation rates of the lunar regolith. And basically what happens is anything that you see in orange or red shows possible water ice and resources at the surface, which would actually be the ideal environment for these rovers to drill. It'd be much easier than actually going deep down into a crater. So then I just overlaid these 2 maps, and I found that there were 3 points that showed possible nearness to resource sites based off of the albedo ratio and the sublimation rates. And when I used the quick map, it turned out that within these 3 points, there was actually areas that had topography that was conducive to an efficient energy site. So these are my 3 sites which I labeled location A, B, and C. And then what determines the location of a thermal body? For this, I had to look at sunlight and temperature, right? And for sunlight, I actually have to look at elevation. So because this project explained, because we're on the pole and the sun is going to hit it at a really oblique angle, the only way to get constant to somewhat constant sunlight is if you're at a really high elevation. And the map here on the left is an elevation map, and anything in red, yellow, or orange shows elevations of 4 kilometers or higher. And then once again, I just grouped what I found. But I also had to look at the average annual surface temperature, because even if we got constant sunlight, we had all the sunlight we needed, if the area was too cold, the thermal body wasn't going to be efficient. So this map right here shows the average annual surface temperature of the lunar South Pole, and anything you see in red or orange shows temperatures in Kelvin that are 175 degrees or higher. And I just overlapped these, and I found that there were 2 locations that had both sunlight and the temperature needed. When it came to thermal body site A, it actually rested neatly on this formation here called Malati Peak, which is actually the highest peak on the South Pole. The thing about Malati Peak, though, is that it's huge. The feasible area for this thermal body was actually 123 kilometers squared, which is way more than what we needed. And here's just a zoomed-in picture on the quick map. But I found that if you look at the southeast end of this mountain, it's actually pretty flat, and it still has the sunlight and the temperatures we need. So I decided to put my thermal body right here, which, by the way, is right next to location A for our energy site, so it's perfect. Thermal body site B, however, was less than perfect. There were a lot of factors that made it impractical. The first being that every single energy site is actually closer to thermal body site A, so it would be pretty irrational to put another thermal body site B all the way up here. And then if you just look at these numbers, the distance to thermal body site B could be as much as 200 kilometers, depending on where the rover is. The approximate travel time could be almost 2 days, and the power that the rovers need to spend just to get there wouldn't be feasible considering the lithium-ion batteries we plan on using. And so with all that in mind, this was the final map that I came up with 3 energy sites situated in kind of a triangle formation in the thermal body site A, right next to the location site A on the northern part of our energy camp. But there are a few glaring holes here, right? And in the future, we're really looking to add an energy site right in the middle, because that would cut the max travel distance of all these rovers by almost half. And also, there's a crater right here called Shackleton, and the rim of that crater actually gets a lot of sunlight. But the thing about it is that it's pretty cold, but I'm confident that as technology increases, we are going to be able to put a thermal body there that's going to be efficient and useful. And just for a little bit of context, this orange box shows what's zoomed in on the left. So there's still a lot of the South Pole that we have to expand to and grow to really sort of capture the entire realm of the prospecting field.
So once we have our rovers and our utility stations and everything up there, we're going to need a communication system so we can actually provide services to our customers. So the first thing that we had to consider for our communication system was what type of satellite we were going to use. So this is a CubeSat. It's a nano satellite that's standardized in size, ranging from, I think, about 10 centimeters cubed in volume. And this is a small sat, which have a range of sizes, ranging from 0.1 kilograms all the way to 180 kilograms. So as you can tell, this is a lot more customizable in size. There's more of a range. We decided we would go with small sats because we wanted that range, and we also were basing our satellite models off of another communication satellite called Malati, which also used laser communications, so it was successful, so we decided we would base our model off of that. Next thing we had to think about was how we would actually have the orbits of the satellites. So we're going to have 3 satellites at 120 degrees apart in a polar orbit with an inclination of about 51 degrees, and an elliptical orbit with an eccentricity of about 0.6. This is because we want to have at least always 2 satellites within the communication line of sight to Earth, so we can keep up constant communications. All these numbers were provided by Todd Eli, the Senior Engineer for Navigation, Guidance, and Control at JPL. We're also going to be using a 0.5 watt infrared laser, once again inspired by the successful Malati mission. Another thing we had to consider was what type of wave communication we were actually going to use. As I mentioned before, we did choose infrared, near infrared, which is lasers, but we originally did consider using radio waves or microwaves. We ended up not doing that because their longer wavelength would cause them to become more scattered, and we wanted a more narrow focus for the long distances we would have to communicate with. So we ended up choosing the laser. This is our satellite, PETI, stands for Polar Encircling Transmission Transferring Infrastructure. Once again, this was designed by Ian on CAD. As you can see, it's powered by these solar arrays on either side. It has a laser transmitter, a receiver, and jet engines to power it. This is basically our communications model. We have our PETI satellites, we have our rovers on the moon that our customers are going to put up there, and we're going to have our receivers and transmitters that we're going to give to them. We're going to have our receiving stations in White Sands, New Mexico, where the Malati receiving stations were also placed. Note the design of these receiving stations are different from the designs of radio wave receiving stations, which are more parabolic in shape because radio waves are broader. But these look more like a telescope because the lasers are a lot more focused and narrow, so they would need to collect that light. And this is basically how our communication system is going to work.
All right, so as a business, we always have to be looking towards the future to stay one step ahead of the game. And what we're really interested in is taking advantage of the processes and resources we can find on the moon to provide energy instead of having to transport everything from Earth. And there are actually a lot of resources on the moon that you could use for energy. Some of them include silicon, which we could use to make solar arrays. There's also a bunch of thorium in the mare, which is like the lava flows on the moon, which could be used for nuclear fission. That's particularly important to us because we are using nuclear fission reactors. There's also a mineral called ilmenite, which is going to be really rich in oxygen, which could be used for fuel. And then there's also something known as the lunar lava tubes. So although the moon doesn't have plate tectonics, it does still have lava flows. And once these lava flows clear out, they leave behind large, like sort of tunnel systems under the surface of the moon, which are cleaned out for us. And they could be sort of a natural safe haven for all our lunar energy systems in our thermal body to protect them from the lunar dust and the solar rays and anything else that might harm them. And then finally, we'd just like to thank Dr. John Gruner for sort of inspiring us and helping us on this journey, and Tom Ramirez for everything he did for us and keeping us safe. That's it.
Okay, so the team is ready to answer questions. Does anyone have a question that they would like to pose to the team? Yes.
So when you're talking about the rovers, are those rovers that are like all designed by your company, or are they rovers that are designed by like other space agencies to fit your specifications?
So we're going to have our own specifications. Like I mentioned before, we're going to have the module with the transmitter and the receiver, but they can use their own rovers as long as it like adheres to what we want.
Other questions?
Do you have like a general idea of what this project would cost?
So these missions aren't cheap; they're very expensive. So it's going to be ranging from about 40 million to 60 million at least.
One other question?
Do you know how much you would have to launch to the moon and what kind of rockets you would have to use to get it up there? How many launches?
So we're not too sure about how we're going to get there, but we did want to use sort of like a pre-plan. We are going to start sending things to these locations that I chose like 5 years in advance, because this is going to be a long process. We do have to build fission reactors on all these sites, which is like hard on Earth, nevertheless in space. We're not sure about like the actual rockets, but we did have a plan of like 5 years before start sending things gradually, and so the payload isn't too large on one rocket.
I have one question. So is your expectation that humans will put this together, or will you use robotics or a combination?
So it was outlined in our concept of operations that we would have robotic assembly done. I don't think it's feasible right now to have actual astronauts putting stuff together.
Okay. Any other questions? Great job. I'm certified to train people and teachers to check out moon rocks. And I know you got to see the big ones when you were at NASA Johnson Space Center, but I'm going to pass around these discs so that you can hold this and you can say, I held a rock that came from the moon, okay? These are samples that the lunar team was discussing. So it shows you stony iron. This is the meteorite sample. This is the lunar sample. So mare soil, island soil, basalt, breccia, all of those. So I'm going to start the meteorite disk here. Most of the meteorites from NASA are picked up in Antarctica. Why do you think? Yes?
Are they well preserved there because of the temperatures?
She thinks it's well preserved. Other? Yes.
They're easier to see in the ice rather than on the darker soil.
Exactly. If you go out to the outside and you look at the soil and you see a rock sitting there and every other rock around it is brown, the chances of you recognizing it as a meteorite are pretty slim. But if you go to Antarctica and you see a rock that's sitting on snow and ice, the chances of it being a meteorite are pretty high. Yes?
Could it also be a geopolitical issue since no one really controls Antarctica?
Well, it could be, but anyone could go out anywhere around the world to pick up meteorites, and there have been some found in other areas. It's just that NASA does a lot of exploration in Antarctica to pick up meteorites because they are easier to see. Okay, so Ian has been fortunate to be selected for the I'm sorry, the Space Settlement Design Competition, which Norm Chaffee talked to you a little bit about. And each of you will receive information about that in the event that it might be something that you would like to participate in. But since Ian is going to be traveling to Kennedy Space Center, I wanted him to come on up. And here's your certificate and your NASA sticker and pin, and congratulations. So we are going to go ahead and give you the opportunity to continue to work with your teams, and you cannot leave this room with my moon disk or my meteorite disk. You can take pictures, that's okay, but I am the one certified, so those have to be in my possession at all times.